In part 1, I demonstrated a method of reducing acid chlorides to aldehydes and got a frankly embarrassing yield of 15%. This video demonstrates a very similar reaction with a much better yield. To prevent borohydride salts from over-reducing an acid chloride all the way to an alcohol at room temperature, they need to be prevented from reacting with the aldehyde. Babler's method, demonstrated in part 1, used pyridine to capture the borane intermediate and stop the reaction midway. This one works a different way by generating a less reactive borohydride compound in situ that only reacts with the acid chloride and won't touch the aldehyde. Where borohydride salts are concerned, the metal counterion plays a major part in determining their reactivity. The harder the metal is as a Lewis acid, the more reactive its borohydride salt is. Sodium borohydride reacts with aldehydes and ketones, but lithium borohydride also reacts with esters. Conversely, borohydride salts of soft Lewis acids like zinc or cadmium are less reactive and also less stable, and can selectively reduce, for instance, imines to amines in the presence of aldehydes and ketones. The pattern of reactivity gets more complicated when aluminium is involved, which forms a covalent borohydride instead of an ionic one, or with transition metals such as nickel, cobalt or copper, where the metal borohydride is so unstable that it decomposes into a boride and hydrogen gas, but that's the basic trend. In 1980, Johnstone and colleagues found that cadmium borohydride has excellent selectivity for reducing acid chlorides to aldehydes. The one real problem with this is that cadmium is highly toxic, on a par with lead or mercury, and its salts are generally hard to find for amateurs. The reaction also requires anhydrous cadmium chloride, which is not as easy to find in general as it's very hygroscopic. Cadmium chloride is almost always sold in its hydrated form. I did actually dehydrate cadmium chloride using the method stated in the paper, refluxing in acetyl chloride, but that was a genuinely horrible job, involving a shit ton of hydrochloric acid fumes, so I've no desire ever to do it again, and I'll not be demonstrating it here. There are several other ways to make anhydrous cadmium chloride, and I intend to demonstrate a useful one in a future video. As in part 1, I'll be demonstrating this reaction using salicyl oil chloride, and as in part 1, I've scaled up the original method to 0.1 moles and modified it accordingly. Now, I've already covered acid chloride formation with cyanuric chloride twice in previous videos, so I'll not show it again. However, I will add that, as I suspected in part 1, refluxing the perchloroethylene extract frees a lot of the acid chloride from the entrained solids and gives a much better overall yield. For a fairer comparison, I repeated the Babler method using the same extraction technique, and I'll make an overall comparison of the two methods at the end of the video. Reagents used were a PCE solution of salicyl chloride, sodium borohydride 3.8 grams, anhydrous cadmium chloride 9.3 grams, DMF 40 grams, THF 40 grams, azeotropic hydrochloric acid 18.5 grams, sodium metabisulfite 28.5 grams, potassium carbonate 28 grams, deionized water 110.5 grams in total, DCM 3 by 20 ml, and sodium sulfate. The PCE solution of acid chloride, which had been cooled in the fridge and contained some solid salicylic acid, was filtered by gravity into an addition funnel. While filtration was taking place, sodium borohydride was dissolved in DMF. Once it was dissolved, cadmium chloride was suspended in THF, the beaker containing the suspension was placed in an ice bath, and the borohydride solution was added to it, causing some effervescence. When the solids in the mixture started to turn grey, indicating the formation of cadmium borohydride, the acid chloride solution was added to the mixture dropwise. During the addition, which took around an hour, sodium metabisulfite was dissolved in 66.5 grams of water, making it up to 30% weight, and potassium carbonate was dissolved in 44 grams of water, making it up to 40% weight. Making the solutions up at this point made good use of the dead time in the process. Once the acid chloride addition was complete, the mixture was stirred for a further 30 minutes, then filtered by vacuum, removing the insoluble cadmium salts. Hydrochloric acid was added to the mixture, neutralising any unreacted sodium borohydride and turning the mixture from yellow to colourless. It also caused some gentle effervescence, which subsided after 15 minutes. The metabisulfite solution was then added to the mixture, causing it to turn from colourless to yellow, and stirred for 30 minutes. The organic and aqueous phases were separated. Because perchloroethylene is very dense, around 1.7 grams per cubic centimetre, the aqueous layer was on top. The potassium carbonate solution was then added to the aqueous layer, causing the yellow solution to lose its colour and a great deal of insoluble colloidal material to form. The milky solution was extracted with 3 portions of DCM, which in this case was the top layer due to the high concentration of salts in the water phase. The interface between the two phases became increasingly difficult to see as each extraction took place. The combined DCM extracts contained a good deal of water and insoluble material. The insoluble material was removed by gravity filtration. Most of the water was removed using a separating funnel. The resultant DCM extract was dried using sodium sulfate, filtered again by gravity, and the solvent was removed first by distillation and then by vacuum. The final product, salicylic aldehyde, was recovered as a yellow oil, almost exactly like the product from part 1. It was mostly odourless in itself, but it left a smoky sweet smell in the residues where it had once stood. The yield was much higher than in part 1. In total, 10.9 grams of product were recovered, giving an overall yield of 89% with respect to salicylic acid. And this is a much better yield than the 50% reported by Johnstone and colleagues. As with part 1, a number of modifications were made to the process, and as in part 1, most of these were due to carrying it out on a much bigger scale than the original method. Much of these improvements were made by applying the knowledge I'd gained from adapting Babler's procedures in part 1. Johnstone's original paper suspended cadmium chloride in acetonitrile. I used THF as in Babler's method because although, like acetonitrile, it mixes freely with water, it's a good deal less polar and it makes phase separation easier during the workup. In the original paper, the acid chloride was added all at once. As in part 1, drop-wise addition of the acid chloride in PCE and the use of an ice bath kept the temperature under control and likely reduced the possibility of over-reduction and side reactions. The original paper used column chromatography to isolate the products. At this scale that's not really practical, so instead I used a metabisulfite extraction to form the bisulfite derivative of the aldehyde, followed by neutralization and solvent extraction. Plus, I hate column chromatography with a passion, and I'll do absolutely anything I can to avoid it. It's a long story. In summary, this is an excellent method, high-yielding, efficient, and a viable alternative to the generally amateur-unfriendly Rosenmund reaction. The only potential sticking point is obtaining and handling the necessary cadmium salts. Now, how does it compare with the method from part 1? As I said earlier on in the video, extraction of the acid chloride was incomplete during part 1, which led to a very low yield. I carried out the reaction again, and the yield improved from 15% to 22%, which is not much, though it is a step in the right direction. To my mind, it's a no-brainer. The cadmium method is simpler, gives much better yields, and also appears to give better purity products. It has one obvious major disadvantage in that it involves using a highly toxic heavy metal salt, but on the other hand, the cadmium salt generated in the reaction is insoluble and a good deal less hazardous than the starting material. And because it's so easily isolated from the reaction mixture, there is definitely potential to recycle it, though this is not a process I've looked into in any great detail. It may well be another potential subject for a future video. But until next time, that's all for now. I hope you enjoyed these 2 videos. Thank you for watching.